In this video, I'm going to solve few problems based on this Diophantine equation. In fact, few word problems. How to solve the linear Diophantine equation using Euclidean algorithm. How problems will come, they may give you set of equations, linear Diophantine equations, and they'll ask you whether it is solvable or not, whether integral solution is there or not, and they may ask you to find all the positive solutions, positive integer solutions of the Diophantine equation, or all solutions of the Diophantine equation, or they may give you some word problems. So I have three equations. First type problem, I have three equations. I have to check whether the solution is available or not. Okay. So first problem, which of the following Diophantine equations cannot be solved? So I have got three equations. Say first equation, that is 6x plus 51y equal to 22. I have to check whether it can be solved or not. Okay. First thing what I have to do is I have to consider this is in the form ax plus by equal to c. I have to consider a and b. I have to find the GCD of these two numbers. Okay. GCD of 6 and 51. What is 6 and 51 GCD of 6? 51 can be written as, I'm using Euclidean algorithm. 51 can be written as 8 times 6 plus 3, right? So that 6 can be written as 2 into 3. Last non-zero remainder is 3, that is the GCD. If this GCD divides C, then this linear Diophantine equation is solvable, means solution exists. Now this 3 does not divide 22, right? Therefore, no solution. Let us take one more equation. Second equation is, say, 33x plus 14y equal to 115. GCD of 33 and 14. You can make out this is 1 in fact. If you can find out directly, no issues. Otherwise, use Euclidean algorithm. 33 can be written as 2 into 14 plus 5. Then write this 14 as 2 into 5 plus 4. Then this 5 can be written as 1 into 4 plus 1. And then this 4 is nothing but 1 into 4. Last non-zero remainder is the GCD. Therefore, 1 is the GCD. And of course, 1 divides 115. So, solution exists. Similarly, question will be check whether it is solvable or not. Okay. And we'll take up another type of problem. Say it's a word problem. In fact, it's a famous problem. 100 fowls problem. It says if a cock is worth 5 coins and a hen 3 coins and 3 chicks together 1 coin, how many cocks, hens, chicks totaling 100 can be bought for 100 coins? I have to write this in terms of equation and then I have to solve the Diophantine equation. Remember one thing, number of cocks, hens and chicks, they should be positive. So I have to be careful while solving, and I have to check whether the general solution is giving me positive values. Okay. So let us denote x. It denotes number of cocks and y is the number of hens, and z denotes number of chicks. First it says a cock is worth 5 coins, okay, a hen 3 coins, and 3 chicks together 1 coin, okay, totaling 100. So for 100 coins he's getting, so equation will be x into 5x, 3 coins per hen, so 3y, and 3 chicks together 1 coin, so can be written as 1 by 3 into z, totaling 100. Then hens and chicks totaling 100 can be bought for 100 coins. So this is for 100 coins, and all number of cocks, hens and chicks together 100. So x plus y plus z equal to 100. Now this z can be replaced. I'm using this equation, I'm rewriting this equation as z equal to 100 minus x minus y, and I'm putting this in this equation so that this will be, I hope you can see, 5x plus 3y plus 1 by 3 into z is 100 minus x minus y equal to 100. Now I'm rewriting this equation. 15x plus 9y plus 100 minus x minus y, and the 3 goes up here so that it will be 300. I'll rearrange this equation. 14x plus 8y equal to 200, so that 7x plus 4y equal to 100. I'm getting a Diophantine equation. 7x plus 4y equal to 100. I have to solve this. First I have to check for GCD. GCD of 7 and 4. Of course we know it as 1. 7, if you want, I'll write with respect to Euclidean algorithm. 7 can be written as 1 into 4 plus 3. Then 4 can be written as 1 into 3 plus 1, and 3 is nothing but again 1 into 3. So last non-zero remainder is a GCD. So GCD of 7 and 4 is 1. Now this now we have to rewrite the equation. GCD 1 can be written as 4 minus 1 into 3. This is 4 minus 1 into 3 can be written as 7 minus 1 into 4. So 4 minus 1 into 7 plus 1 into 4. 1 into 4 plus 1 into 4, that is 2 into 4. 2 into 4 plus this can be written as minus 1 into 7. My equation is should be in this form. 7x plus 4y equal to what was the equation? 100. So I have to rewrite this. This can be written as 7 into minus 1 plus 4 into 2. Okay. Now the left hand side is 1, but here the right hand side is 100. So I need to multiply this equation by 100. So that I'm getting 100 equal to 7 into minus 200 plus 4 into 200. I'm sorry, this is 100. This is 200. So I'm getting here this x value, x naught as minus 100 and y naught as 200. Okay, here I'm getting negative value of x, so I cannot take it as a particular solution for this equation, because we know x denotes number of cogs and it should be positive. So if I consider this as a particular solution, then the general solution turns out to be x equal to x naught plus a by d into t. That is x naught plus a by d into t. So this will be 4t, and y is y naught minus b by d. b by d turns out to be 7t, right? Since x and y must be positive, so this value should be greater than or equal to 0, and again this has to be greater than 0. So when this, to make this is greater than 0, 4t is greater than or equal to 100, so t must be greater than or equal to 25. Okay, similarly this must be positive, so this can be made 70. If I take it over here, then it is reversed, so that 70 must be less than 200, so t must be less than 28, I can say, right? And third condition, what happens to z when I put x and y as this? Z is 100 minus x minus y. So 100 minus x is minus 100 plus 4t minus x minus y minus of 200 minus 7t. So this will be 100 plus 100 minus 40 minus 200 plus 70. So that z is 3t. Now again this should be greater than or equal to 0. So this is possible if t is greater than or equal to 0. So I have got 3 conditions for t now. So t must lie in between, I can write it as t should be greater than or equal to 25, and it should be less than or equal to, or less than in fact, 28. So we'll make a table now. Put t values 25, 26, 27 and 28. We'll find the values of x and y. So when t is 25, x value is, in this equation, I'm getting t is 25, then x value becomes 0. Then here I'm putting t value as 25. So that the value of y is 25 and value of z becomes 75. So like that I'll fill the table. You have to put values for t in these 3 equation x, y, z. These 3 equation have to put and have to get the values of x, y, z. So those will give me the values, and so this is the condition, and you are getting different values for x and y and z. So to write the general solution, I have to take the initial value, that is particular solution, as this x as 0 and y as 25, so that z is 75. How to write the equation? We know general solution. We know x equal to x naught plus a by d into t, and y is equal to y naught minus b by d into t. So x naught I'm considering as 0 plus a by d into t, so this will be 4t, and y equal to y0 as 25 minus 7t. So the general solution is x equal to 4t and y equal to 25 minus 7t, and z comes out to be 75 plus 3t, where t is an arbitrary integer or any integer. So if x is given 4, then value of y will be 18, z will be 78, like that. So these three should be greater than 0. Problem number 4. A certain number of 6s and 9s is added to give a sum of 126. The number of 6s and 9s are interchanged, then the new sum is 114. How many of each were there originally? So again a word problem. Let us say x denotes number of 6s and y denotes number of 9s. First equation is a certain number of 6s and 9s added to give sum 126. So 6x plus 9y gives me 126. And if the number of 6s and 9s are interchanged, in the sense 9x plus 6y, then the sum comes out to be 114. Okay, what was the original number of 6s and 9s? So first equation is 6x plus 9y equal to 126. I have to find the GCD of 6 and 9. I use Euclidean algorithm to find the GCD. So GCD is 3. Since 3 divides 126, there is a solution, and thus D can be written as 9 minus 1 into 6, and thus same as writing 6x plus 9y. In that form I have to write, so 6 into minus 1 plus 9 into 1. I want right hand side to be 126, so I'll multiply this whole equation by 42, so that this is 126. 6 into minus 42 plus 9 into 42. If I consider this, then x is minus 42 plus b by d, so it is 3t, and y equal to 42 minus 2t. X and y denotes number of 6s and number of 9s, so they should be greater than 0. Okay, when I apply that, then the positive solution for this, I'll get 3t greater than 42, so that t is greater than 14. Here minus 2t greater than minus 42, so that 2t is less than 42 and t is less than 21. So the value of t must lie in between. It must be greater than 14 and it must be less than 21. So I have to write the values of t, x, y and z. Initial value, if I give t as 14, then I'm getting x as 0, greater than or equal to, in fact. Okay, so when I give t as 14 in this, 14, then the x value will comes out to be 0. When x is 0, y value is 14, and you'll get some z value depending on the equation. So particular solution, I'm considering it as this. So I'll rewrite x as 3t and y as 14 minus 2t. Then find the value of t. I have to find the value of t such that it is interchanged. 6y plus 9x equal to 114. So 6y is 14 minus 2t and x is 3t, should be equal to 114. So 6, so this is 15t minus 30, I guess, so that I can write it this side, minus 30 equal to 0, 15t equal to 30, t equal to 2. T equal to 2. When I apply that, x naught is 3t, t equal to 2, so that x naught is 6, and y naught is 14 minus 2t, so it is 14 minus 4, so it is 10. So initial, it is asked what are the original number of 6s and 9s. So x is 6 and 6 6s and 10 9s.